Hello, welcome to our new course. This is CS 21004, Formal Languages. And Automated Theory. Also known as FLAT. We two teachers will handle this course, me and SK, Professor Sudeshna Kolei. Okay, so it is a 310 course. So we have plans to upload 3 hours of recording and 1 hour of tutorial, and if needed, some doubt clearance. So this is given the slot F4. So for doubt clearance and tutorial, we will use the Friday slot, which is 11 AM to, I would say, 12 noon. If needed, a little bit more. Okay. So, as this is an online semester, we have to go for continuous evaluation, and as usual, as we have done in the last class on discrete structures, we will have something like 3 to 4 short tests, and let's say another 3 or maybe at most 4 long tests, and if needed, 1 or 2 programming assignments. Perhaps in this course, programming assignments make a little bit more sense than in the discrete structures course. Whatever it is, so we will shortly tell you the schedule of this test, roughly at least. Fortunately, this is not a very short semester, and therefore we will more leisurely have these tests compared to what we had in the last semester. And I hope you will enjoy this space and this so-called normal semester schedule, 3 hours of recording, 3 hours of teaching, 1 hour of tutorial, things like that. We will more or less strictly follow this book, Dexter Cozen. He has written many books, so this is the book we will follow: Automata and Computability. So this, by our understanding or preference or choice, personal choice, is a very good book, and also it has a good set of exercises. Some tutorial exercises and some general miscellaneous exercises. So we will solve some of these exercises in the tutorial sessions, leaving the rest of the things to you. Okay, so this is the overall plan for this course. Today that is in the first lecture, I will give you a very broad description of what we are going to do in this course. So, I need to, okay, good. So this is, I would say, why this course. This is an important question. I briefly describe this background, and then we will switch to some paradigm of what we will do throughout this course. So it's basically to understand ourselves as computer scientists. So, of course, we know what a science is, broadly. So, the question that we will address in this course and also in your theory of computation course in the next year is what is meant by computation. Another associated and related issue is what is at all computable and what is not. And an associated question that will naturally arise is everything computable? And we will soon see that the answer is a big no. Okay, so historically, the notion of computability came into existence when the celebrated mathematician of the late 19th and 20th century, David Hilbert, in a convention in 1900, proposed a set of open mathematical problems these are very interesting and important mathematical problems, and Hilbert told in this convention that these are the sequence of problems, a set of problems that is the most important for mathematicians to solve in the new 20th century. Among this, it was actually a mathematical problem, but this may be considered a formal conception of the notion of computability. So it's called the Hilbert's tens problem. In German, Hilbert was a German actually. It is called Entscheidungsproblem. In English, you may call it the decision problem in a literal translation, but we will soon use the word decidability instead of decision, because we will use this decision thing for a technical term, related of course. So it's basically the problem of decidability. So he essentially mentioned about a mathematical problem whether there exists a something like or an effective computation procedure for solving some problem. I am not going to the details of that problem because it's not exactly very relevant, at least for the moment. Okay, but there is an effective computation procedure. So that thing, which is known as effective computation, he just mentioned this, but what is understood by this? Okay, now what happened? After this, there were several paradigms that were designed in order to capture the notion of effective computability. So in the earlier days, maybe first few decades, first 2 or 3 decades, people talked about some formalisms like lambda calculus, theory of mu recursion, and then something like post problems, and even something called unrestricted or type 0 grammars. Finally, in mid-1930s, the British mathematician Alan Matheson Turing proposed the concept of Turing machines. So they are all proposed in order to quantify or scientifically make it precise to talk about effective computability. These are all mathematical formulations, and they look quite, I would say, distinct from one another. So Turing machines we will study. They are the only, I would say, paradigm that looks like machines. Okay. Other things are not exactly like machines. But what turned out is that, and of course, there are many other things. And today, of course, you can write things like C programs, okay, or C++ programs, Java programs, and all that, any high-level language program, or even assembly language program. What is important in this context is that all these different looking paradigms, they all encompass essentially the same notion of computability. Okay, so this sameness in all these different paradigms leads to something called Church-Turing thesis. Thesis essentially means here is hypothesis. So each of these paradigms, lambda calculus or mu recursion or Turing machines or C programs, they define whatever is computable. About a century after Turing's proposal, at least 80, 85, 90 years, something like that, we have not yet come up with some paradigm which can outperform these known paradigms. So the Church-Turing thesis apparently holds. And we will get introduced to this Church-Turing thesis via our exposition of Turing machines. Okay. We will come near the end of this course, what is meant by computable, what is meant by not computable, with examples, and how do you prove that certain things cannot be computed. But today, I start with a kind of formalism. Okay. So, a formal treatment of computability. Okay, so there are several nitty-gritties here, but cutting the long story short, we eventually have a thing like this. Suppose that you have a universal set U. Such that I will assume that every element of U has a finite presentation. So I will come to this finite presentation thing very soon. And you are given some subset A of U. Some subset. Okay. So how you specify A? That's an interesting and important thing. I will come to that next. And then you are given an element X in U. Formally, so since every element U has a finite of U has a finite representation, better I would say representation. X in particular also has a finite representation. And the formal way of defining a computation is to decide whether X is an element of A. Okay. So this may look a little bit like a loss of generality, but in practice we can see that this is not exactly a loss of generality. In particular, you would like to say that you want to compute certain functions from A to B. Well, A to B, and for such decision problems, this B is nothing but 0 or 1. Or you may call it true and false, or false and true. Or yes and no, something like that. It's a particular type of functional problem, but still only our ability to solve binary valued or compute binary valued functions is already good enough to define computations. And this is not only exactly a loss of generality. Most of the problems, computational problems, can be rephrased in terms of equivalent decision problems. And as such, this formalism has stood the test of time. So we will follow this. Given some universal set U, such that every element of U is finitely representable, and some subset A, such that, okay, so another important thing is this. A must also be finitely specified. I will come to some examples to explain what is meant by some subset is finitely specified. Okay, there you are given an arbitrary string x of u. Your task is you just decide whether that string x is a member of A. Okay. For that, you have to use the finite specification of this set A. Okay. Fine. So, this is broadly what we will do. So, now let us look at this question. How to specify A finitely. Okay. So, one possibility is we can have an English language description. Of course, this description must fit in a finite amount of space. We may also have some mathematical description. Again, this is also mathematical, but anyway, we can say using a set of rules which are usually recursive. Okay, we will see lots of examples today. And also what we will do, we will do some kind of computing machines to represent these sets A. Okay. First of all, note that if A is finite, a finite set, then A can be exhaustively enumerated. Okay. But if A is not finite, then we need some formalism to fully characterize all the members and only the members of A. Okay. Okay, so if it is finite, it may contain a huge number of elements, but in principle, we can write all the elements of A one after another and specify A explicitly. If A is infinite, of course, this is not possible. So we have to use some other ways of doing it. Okay. So, U is the universal set. And A is a subset of U. For a reason, for the moment it's not clear, A is often called a language. Okay, this name may be a little bit problematic with this abstract introduction, but somewhat this is related to something like the English language, some human language like English. And we can specify an English language using its grammar, which is a set of rules, how to form sentences. Set of rules. Okay, grammatical rules, plus some kind of vocabulary. Okay. Anyway, we will not talk about English language and similar things today. We will talk about what is called the language or languages of numbers. Okay. To make things more precise, I will mostly restrict our numbers to set of natural numbers, that is 1, 2, 3, all positive integers. In some cases, we may also have to include 0 in our set of natural numbers. So it's 0, 1, 2, 3. And we may also use integers, negative integers, include negative integers also, like this. For the moment, number will indicate either a positive integer or a non-negative part is positive integer or something like all integers. Okay, so these are basically language of integers. Okay, so given this, we see that a language of numbers is a set of integers, maybe positive, non-negative, things like that. Okay. So we know that N, N0, Z, they are all countable. Whereas the set of all languages of numbers is nothing but the power set, maybe of N, let's say, or N0, Z, whatever. Now, by the power set theorem, this is not countable. Okay, so we have seen this power set theorem, right, in the discrete structures course. And the immediate implication of this is that not all languages can have a finite representation. Okay. Some of these do have. Okay. And I would say we are, for all practical purposes, we are interested in these languages only. In fact, there are many other languages which we do not know how they look like. But still, among those things, there are, in a sense, languages that are not computable. Okay. Some do have, most do not have. And somehow, we have to find examples of I should not write this actually. Okay. If we cannot represent something using a finite amount of space, we cannot do anything about those. Okay. So, we are interested in those which can be represented. And most important thing is this: among these languages, some will introduce the notion of uncomputability. Okay. Well, this is, I believe, still a bit too much abstract. Let us look at quite a few examples. So, we know that our universe for the moment is a set of natural numbers, including or excluding 0, or set of integers. So we know that each integer has a finite representation. Like decimal representation with possible sign, binary representation, hexadecimal, octal, and so on. Okay, to some base. Okay. And by definition, every natural number or integer, positive or negative, is finite, and therefore this is a string of decimal digits or binary digits, optionally followed by a sign. These are all finite representations. Okay. So let us look at some examples, interesting examples of numbers. How we can formally describe a subset of this U. Okay, so maybe we start with one example. Maybe E, the set of even natural numbers. Okay, so 2, 4, 6, if I just omit this 0, and so on. How do I specify this? Okay, so a mathematical way of specifying this language is something like this: 2 times n, such that n is a positive integer. So you see that this is a mathematical finite description. So this is, I can call it a mathematical description. Which fits in this finite amount of space. Whereas this I can call an English language description. This also fits in a finite amount of space, whereas this is not a finite representation. Because we do not know what ... stands for. Right. Okay, so now given an integer, so this is a representation. You can see there are two finite representation, one in English language, the other one in some mathematical, using some mathematical notations. And given x in n, how to decide? This is the language membership problem. Decide whether x is in E. Okay. So how do we do it? Maybe it depends upon which representation you take for integers. If it is a binary representation, then x must end with 0. If it is a decimal representation, x must end with 0 or 2 or 4 or 6 or 8. Okay. So this is an example a very simple example of a language of integers. Okay, so let us look at a second example. P. You can see 2, 3, 5, 7, 11, 13, and so on. Of course, this is not a finite representation, but this is an English language description of this set, the set of all primes, with our understanding what we mean by a prime. Okay. And to check whether an integer x belongs to P is nothing but the primality testing problem. Okay, so how can primes be defined? Using rules. We will not do it now, but at least we have an English language short description of this, which is this. But this is not a finite description, once again. Because it uses this ellipses. Similarly, you may talk about maybe these perfect squares. Okay. This is a finite description, and how do you check the membership? So you compute the integer square root a of x, and then check whether x is equal to a square. So this is an algorithm. Okay. Okay. Likewise, you can define the powers of 2 and maybe n0. Okay. And once again, checking whether something is the power of 2 is not really that difficult. Okay. So let us look at then a set of little bit non-trivial examples. So how many have I? 4. Okay. Okay, maybe something like this, Fibonacci numbers. So maybe I define it as F, the set F, 0, 1, 2, 3, 5, 8, 13, and so on. So this is once again not a finite representation, but I can write it this way. N, okay, F n, the nth Fibonacci number for some n greater than or equal to 0. Okay. Now, this is of course a finite description, but I have not defined this f sub n yet. So, this actually says, so rules to generate these individual members Fn. So this is standard recursion, right? You specify two small things, f0 equal to 0, f1 equal to 1, and subsequently fn equal to fn minus 1 plus fn minus 2, the standard Fibonacci recurrence for n greater than or equal to 2. So this you can see is a finite description, and this is recursive. Generate, or for that matter define, all Fibonacci numbers. Okay. So I've given x in n to check. This is the language membership problem, whether x is in f, that is x is equal to fn for some n. So one possible way of doing it, keep on generating f0, f1, f2, fn until fn, you know, this is basically an increasing sequence. Okay, until fn is greater than or equal to x. I'll check whether I did not say this is the most efficient way of doing it, but this is definitely an algorithm. Check whether the largest number generated less than or equal to the given, okay, I would say until fn, maybe it's not exactly very correct thing I have. Better let me write this way. So long as this is less than or equal to x. Once it exceeds x, there is no point moving further. Okay, and the largest Fibonacci number that you have generated using this formula, recursive formula, you just check whether it is equal to x. If it is equal to x, then the given x is a Fibonacci number. If it is not equal to x, then x is not a Fibonacci number. So this is an algorithm for doing it, not necessarily the most efficient. Okay, maybe a few other examples. Okay, maybe this one. Happy numbers. This family is also specified by a procedure, a rule. Okay. Maybe I start with something like, let's say 21. What I do, from this I will generate the sum of squares of its digits, which in this case is 5, right? 5. Then I keep on repeating this, 5 square, which is 25. Once again I repeat it, 2 square plus 5 square. So how much is that? 29, right? 29. From this I generate 2 square plus 9 square. So this is 4 plus 81. Yeah, 85. Then what is this? 64, 25, 89. Okay, equal to. From this I generate, yes. Let me just work it out. I just clean it a little bit. Here I generate 8 square plus 9 square, which is 145. After this, 1 square plus 4 square plus 5 square. This is what? 42. Then 16 plus 4, 20. 22, 2 square plus 0 square, 4. Then 16, 4 square is 16. 6 square plus 1 square, 37. Then 3 square plus 7 square, 58. Then 5 square plus 8 square, which is essentially the same as this. So you get the same thing. So this is same as this. Okay. So if I repeat this procedure, I will eventually end up in a loop. And what is that loop? So typically you usually start with this 4, 16, 37, 58, 89, 145, 42, 20, and once again back to 4. Okay. So such numbers, I started from 21, I eventually ended up in this loop. So this is called an unhappy number. Or also called a sad number. Whereas let us look at what happens if I start with 23. Is it a good example? Yes, 23 is a good example. Let us do the same thing. What is this? 4 plus 9, 13. 10. 1. Subsequently, if you keep on doing this, it will be 1, 1, 1, 1, 1, 1, 1, 1. So this 23, which does not encounter such a looping behavior, but eventually reduces to 1, this is called a happy number. Okay. So the reason for me to introduce these happy numbers is here a procedure describes or specifies the happy numbers or the unhappy numbers also. Okay. So it's a kind of recursive procedure, but it's basically an algorithm. Okay. So this procedure actually can be specified using a C language or even in English language by a small program, small function, recursive function. And such procedural descriptions of languages are also allowed because it's these are after all finite descriptions. Okay. Now definitely, since this is a recursive procedure, okay, so is happy n if and only if n is 1, it has reduced to 1, or is happy, let's say sum of squares of the digits of n. Okay, so this is a recursive call. Okay. Now, in order that I make it an algorithm, okay, so I must have some termination. Okay, definitely if we eventually end up here, n equal to 1, this is definitely a termination criterion. Otherwise, looping. Okay, we have to detect this looping for unhappy numbers. Okay, definitely we can actually keep a list of numbers generated so far. And whenever you get a new number using the sum of square thing, you can find out. This is generated already, so we have entered a loop. Okay. Now I leave it to you as an exercise, not so difficult. Every unhappy number falls into the loop involving up, four. Prove it. Okay, so that means if you start with any unhappy number like 21, you will eventually end up in this loop, 4, 16, 37, 48. So that essentially implies that I can take the termination condition. N either reduces to 1 or n reduces to 4. So if this is the case, the original number is happy. If this is the case, the original number is unhappy. Okay. There are many examples I may continue with. Maybe another example, maybe not too bad. Maybe I will take these numbers. What is our example? Maybe this is the 7th one. Incidentally, if I just go to the previous page, we may simply ask the questions. Which years are lucky? Is 2020 a lucky year? We definitely know it is not. Unfortunately, 2021 is also not happy. In fact, so far in this millennium, which are the things? 2003, 2008, 2019, 2026, 2030. These are happy. Okay, but after that there are definitely some 20-something. These are also happy, but okay, so the next happy year is coming only in 2026. Okay. Anyway, don't worry. We will all be happy in 2021 itself. Okay. So now let us look at this. Maybe let us look at this SPH. Set of all products of the form PQR such that PQR are distinct primes. Okay. For example, 2 times 3 times 5, that is 30. Then you take 1001, which is 7 times 11 times 13. And okay, maybe I have to work this out. I do not remember fully. I believe 2020, 2022, 2 times 3 times something like 3. 77 maybe, or 337. 337. So these are sphenic. 60 is not, because also if I take 210, 2 times 3 times 5 times 7 are not sphenic. Okay, so an algorithm to check whether X is in this set, what can you do? One possibility is factor X. Okay. So doable in finite time, although it's actually not a practical problem, I mean a problem that can be practically solved, but anyway it is doable in finite time. Okay. So these are all examples of languages of numbers that can be solved algorithmically. So let me give you just a hint that not all languages are computable in that sense. Okay, but for that, let us look at this, the iterated logarithm function. Okay, so let us say, when I say log, I mean log to the base 2. Okay, so you start with some number n, take log of n, take log of n, and so on until we get a value less than equal to 1. So for example, log of 2 is 1, log of 3 is something like 1 point blah blah blah, and if I take another log, this becomes less than 1. Okay, because it's smaller than 2. Okay, so I say that log star 2 is 1 because I needed only one iteration of this loop. I have to take only one log in order to reduce this thing to 1, whereas log star 3 is 2. What is log star 4? 2. Log of 2 is 1. So log star 4 is also 2. Then if you check log star 5, that is 3. So initially it's an interestingly increasing sequence, but if I ask you the question, find the smallest n such that log star n is 4. Okay, you will see that this is nothing but 16. One logarithm will give you 8, next one will give you 4, next one will give you 2, next one will give you 1. So smallest n. And what about this? Log star n, smallest n, for which log star n is 5, that is 2 power 16. 216, then 8, 4, 2, 1. And what about this? Equal to 6. It is 2 power 16. Okay. And so on. Now this is a pretty huge number. It's something like 2 power 6, 5, 5, 3, 6. This quantity. This one. And you do not imagine how big this quantity. This is greater than the number of for example, electrons in the known universe. Okay, sorry, maybe I write it a little bit neatly. Number of atoms, number of electrons, whatever you say. So it's a huge number. So if I now define this set, maybe iterated log n, or maybe why should I use n here? Just IL. But n, or the set of all x, such that log star x is equal to n for some n in n, and x is smallest among those numbers y, such that log star y is n. Okay. So for example, if IL0, IL1 is 1, 2, IL1 is 2, right? Sorry, 1. IL2 is... Did I make a mistake? Let me see. Let me go to the previous page. 4 is 2. Maybe I'm making a small mistake here somewhere. I see. 5 is 3. 8 also it is 3, right? Okay. So maybe this is something. Okay. This is 2. This is 1. Log star 8 is 3. Okay. So this is not the smallest, largest. Yeah. Is the largest. Okay. Anyway, whatever I mean, you can find out. I will go here. So this is not smallest, this is largest. 2. IL3 is 8. IL4 is 16. IL5 is 2 power 16, which is 65536. IL6 is 2 power of 65536, and it's a huge number. In general, ILN is equal to 2 to the power ILN minus 1. So in other words, this sequence can also be recursively defined. Although, you can see, it's a very, very fast growing function. Okay, but still it can be defined recursively. Okay, so very, very fast growing. But still it can be defined recursively, and therefore it is in a sense computable. So now let us look at, maybe I have made the correct numbering. 6. Okay, fine. 7, 8, 9. I cannot define this for the moment, but I just BBN. Okay, so this can be defined using Turing machines. Let us see. If we get an opportunity, we will define it. So the idea is that these numbers, BZB over n, grow so rapidly with n that computers cannot keep track of them. So these are what are called uncomputable numbers. One example. Okay. So how it is defined, that this requires some formalism. Right now I cannot do it. In fact, it can be shown that if n is any computable function of positive integers, then this busy beaver function n grows faster than f of n, any computable function, and therefore it is not computable. Okay. Anyway, so there are interesting examples like this of several numbers. I had a few other examples, but I think I can skip all these things. I've already taken quite enough time. So the next question, this should actually give you an indication that various types of computational problems may be defined using languages. But so far we have considered only languages of numbers. Okay. Why should we restrict only to numbers? We may also talk about languages of sets. Of course, finite sets anyway, I'll come to that. Maybe languages of polynomials, languages of graphs, and so on. Okay. So numbers are not the only important things to us. Sets, let us call it finite sets, maybe for the moment. Languages of sequences, maybe. Okay, things like that. There are many things which we may need to consider in computation while defining computations, not only numbers. Graphs, for example, are an important tool in computer science. So we will encompass all these things to something called languages of things. The thing may be something of importance to us, like numbers, sets, polynomials, graphs, sequences. Okay. And maybe the universal set of things. Of course, as I mentioned earlier, each thing must have a finite representation. Okay. And then you are given a finite representation, a finite specification of a subset A. Okay. So some finite specification is given. using one of the techniques. English language, or using rules, or using a procedure, or using some algorithm machine, something like that. Okay. And then if you are given an x in U, decide whether x is in A. Okay. So this is the generic model of a computational problem. Okay, so this is a generic model, what we understand by computational problem. It's essentially a decision problem which has to do with language membership. Okay. Now, in order to make things simpler, we almost, if not all, everything that has a finite representation almost anything under the sun or in our head, whatever, has a finite encoding as a string. Okay, with some symbols. Okay, finite encoding. Okay, for example, if I look at integers, natural numbers, so these are binary representation, is a sequence of zeros and ones. This is a finite string. Sequence of 0, ones. Okay. Again, if I look at a graph G, V, with V equal to N, then I can simply have 1, 1, up to 1, N times, followed by 0, followed by maybe let's say n square bits. Okay, so this is basically the adjacency matrix of the graph in the row measure form, for example. Okay, for example, if I look at this graph, maybe this graph, and let us give some name, 0, 1, 2. Then I can say there are 3 vertices, 1, 1, 1. Now this 0 acts as a separator. Then I have a 3 by 3 matrix. For vertex 0, it is 0, 1, 1. For vertex 1, it is 1, 0, 1. Vertex 2, it is 1, 1, 0. So this is a finite representation of this graph as a binary sequence. Okay. So this we call a finite encoding of this picture, which is this graph. Okay. Since every such thing, or almost every such thing in which we take interest, can be represented using a string, the good thing that we will do to start with, we will use strings and only strings to define languages. This essentially means, if I go to the previous slide, I don't need to worry too much about whether it's numbers, sets, polynomials, graphs, sequence, or any other thing. We will define languages of strings, and under some implicit encoding scheme in our head, we can represent everything like this: languages of numbers, languages of graphs, languages of polynomials, and so on. Even languages of Turing machines. Okay. Therefore, what we are going to do in the next class is something good enough for defining languages and computation problems, although they may initially seem a little bit contrived, but they are good enough. Anyway, I think I have taken much longer than 1 hour, so let me stop at this point of time. So we will continue with a more formal introduction to this course in the next lecture. Okay, so see you.